So moving on to the double angle identities for sine, what we're going to end up doing here is a whole bunch of trig identities where you have a sine function that has two things in its argument, either two variables or one variable and a measurement in radians. And we're going to use these three little puzzle pieces in order to tear the problem apart. Now, if you scroll down below the video on the web page, you will find a geometric justification for all three of these things. So if you want to see why this is true, you can scroll down and read through that, but I'm not going to spend any time talking about it. Because what we need to be able to do with this is to use it primarily. So I'm going to draw your attention to this particular expression here, which seems pretty heinous. You wonder why that would ever happen. But this sort of thing occurs quite frequently in physics and engineering problems. So I have a function up there that I'm supposed to solve, right? I know the answer and I need to find the value of phi that makes it work. But the problem is I have two functions in here. I have a sine and I have a cosine. And algebra won't let you operate on two different functions at the same time. You have to be able to collapse them into one. It's very similar to like common denominator. You can't flip a fraction unless you've put all the fractions together. So I have to have a way to take this mess with two functions, a sine and a cos, and bend it into a single sine or a single cosine. So I'm going to use these as the key for how to do that. You notice I have a sine of something, cos of something, minus a sine of something, cos of something. Well, that looks like this one here in the middle, right? I have a sine cos minus a sine cos. So I'm going to take this little structure here and I'm going to try and bend it into that. So to do that, I'm going to have to recognize that the alpha, right, this piece, is going to be the pi over 3. So I've got cos pi over 3 and sine pi over 3. And the beta, the second thing here, is the phi. So what I'm going to do with this mess is say that because of that, then, that sine pi over 3 cos phi minus sine phi cos pi over 3 is equal to this thing, sine of my alpha, which was pi over 3, minus my beta, which was phi. And that whole thing is equal to negative 0.4. So what have I accomplished here? Well, I don't need this anymore. I can just work on that. That sine of pi over 3 minus phi equals negative 0.4. All right, so I've taken this really monstrous equation here and I've rendered it down to a single sine. And now I just have to solve this using the normal techniques I've been using. So I'm going to have to pull an arc sine, pull that over to the other side, so that pi over 3 minus phi is the arc sine of negative 0.4. So if I plug this into the calculator, so I'm checking, 0.4 is not one of my special triangle ratios. So I'm going to turn this thing on, make sure she's in radians. Arc sine of negative 0.4 gives me negative 0.412 radians plus 2 pi n. Or, if I'm going to do the second solution, using cast rule, sine ratios are negative down here and over here. And I just got negative 0.412. Well, that's this one, negative 0.412. So I need to get over here. The way I'm going to do that is to go pi radians plus 0.412. That, of course, that's no different than what we've been doing in all of the previous sections. So the resolution of my arcsine is either this answer or this answer, and both of those things are equal to pi over 3 minus phi. So I just need to go through and solve now. I'm going to subtract pi over 3 from both sides. Because I can't write this as a fraction of pi, because it wasn't a special triangle answer, I'm going to have to actually do pi divided by 3. So negative 4 minus, where is the pi on this button? Pi divided by 3 is negative 1.459 plus 2 pi n. And that's negative phi. I don't want negative phi, I want phi. So I'm going to multiply through by negative 1. I get 1.459 plus 2 minus 2 pi n. Alright, lovely. Now, for this solution, same thing. I'm going to subtract pi over 3 from this side. Pi plus 0.412 minus pi over 3 plus 2 pi n minus phi is here pi plus 0.412 minus pi divided by 3 gives me 2.506 plus 2 pi n. And again, I don't want negative phi, I want phi. So phi is negative 2.506 radians minus 2 pi n. Lovely. So at this particular value in radians, this number plus or minus as many 2 pi's as you like. If I put that here and here, I would spit out negative 0.4. So I've found one set of values, and I found the other set of values that will also make that true. And I wouldn't have been able to do it if I hadn't been able to take this complicated expression and render it as a single sign. So that is the purpose of these things, is to take things that are unnecessarily complicated with many sine and cosine pieces and boil them down into a single sign. Now the next section will have another set of puzzle pieces that allow you to render down into a single cosine, but we'll leave them for a minute. So I'm just going to erase this, and then we'll try a slightly more complicated example. Okay, so again, I'm trying to solve for a value of phi so that this equation is worth a half. But I've got a sine and a cosine in there. So I can't use arcsine because cos is in the way. I can't use arccos because sine is in the way. So I have to find some way to collapse those two things so that I can write them as a single sign. Now that it doesn't look like the last one. The last one had a sine times a cos plus a sine times a cos. So this one's a little funny. I'm going to have to do a little bit of manipulation. So the first thing I'm going to recognize is that I have a root 2 there. Now when you're dealing with sines and cosines and you see a root 2, that's not an accident. That's one of the special triangle values. So I'm going to use that fact to try and construct a cosine to attach to this and a sine to attach to this so that I will have the right Lego bits to be able to collapse them down. So first thing I wanted was a sine times a thing, right? Like I've got a plus sign. I want a sine times a thing plus a sine times a cos, or a thing times a cos. So I'm going to write this as two fractions first off. So I'm going to go sine phi times 1 over root 2 plus 1 over root 2 cos phi. All right. Now I'm going to recognize in my brain that 1 over root 2 happens to be the cosine of pi over 4, and 1 over root 2 happens to also be the sine of pi over 4 by special triangles. So in this front piece, because I see a plus sign and I see a plus sign there, I'm going to try and build this little structure here. I already have the sine. I need a cos attached. So I'm going to write this as sine phi cos pi over 4 plus, and in the second part I need a sine of something times a cos. I already have the cos, so I'm going to use this. And now that I've done that, the phi looks like my alpha piece, and the pi over 4 looks like my beta piece. So this whole thing is going to collapse down into the sine of phi plus pi over 4. So that's the expression I need to solve now. So net, and this is all that's new in this section, is that when you see something gross like this with a sine and a cosine, you have to go look at your double angle identities and see which one of these three tools is going to be most useful to bend this into a single sine. From there, we solve it just like normal, which I'll go through so you can see. I've got to toss the sine over there, so it's an arc sine. Means I've got phi plus pi over 4 equals arc sine of 0.5. Now 0.5 is a special triangle value. Right, 1, 2, root 3. This is pi over 3. This is pi over 6. So arc sine of 0.5, the sine ratio, so opposite over hypotenuse would be, that would be pi over 6. No, I guess that splits, doesn't it? So one of them is pi over 6 plus 2 pi n. And using cast rule, this is a sine ratio that's positive, so one of them is in this quadrant, one's in that quadrant. Pi over 6 is this one, and this would be not quite a full pi, so that's 5/6 of pi. And each of those things are equal to phi plus pi over 4. So I just have to subtract pi over 4 from each side. see, common denominator between that would be 12. So 2 pi over 12 minus 3 pi over 4 would be minus 1 pi over 12 plus 2 pi n. That's just common denominators. If you're not sure, actually exchange them so you can see. Over here, 5 pi over 6 minus pi over 4 plus 2 pi n. Phi would be it would be 10 pi over 12 minus 3 pi over 12, which would be 7 pi over 12 plus 2 pi n. There you go. Those two particular values in radians plus as many rotations as you like would satisfy this particular equation. Okay, so last example, I have sine of phi equals root 3 times 1 plus cos of phi. Now that doesn't look like any of these things. The only thing that it has in common with these three expressions is it has both a sine phi and a cos phi in it. So I have to figure out how I'm going to manipulate this in order to make them look this way. Okay. So the first thing I'm going to do is I'm going to expand this root 3 into the cosine, because none of these look like they have a 1 plus cos in them. So I'm going to toss this onto here and onto there. Equals root 3 plus root 3 cos phi. And root 3, that's another tricky one, because it's a special triangle value. It shows up as a special triangle result for tan. When it's mixed with sines and cosines, it ends up as root 3 over 2. Right? If you draw your triangle there, 1, 2, root 3, pi over 3, pi over 6. Root 3 over 2 would be the sine of pi over 3, and root 3 over 2 would be the cosine of pi over 6. So I want root 3. I want root 3 over 2. And there's nothing stopping me from making that. I just have to make sure I divide everything by 2. Okay, that's encouraging. So the sines and the cosines in these double angle identities are supposed to be together. So I'm going to pull this over to the other side. So I end up with sine phi over 2 minus root 3 over 2 cosine of phi equals this root 3 over 2, which I've left alone. Well, I've got a subtraction here, so I'm working with this center line. I have a sine of something. Root 3 over 2 is the sine of pi over 3. So I could replace that as sine of pi over 3. Now I have half of sine theta. Well, 1/2 is the sine of pi over 6. It's also the cosine of pi over 3. I'm already working with pi over 3, so I'm going to stick with pi over 3, so I don't end up mixing all my angles. 1/2 is the cosine of pi over 3. So I've got sine theta here, sine phi, and the cos of pi over 3. Well, I've done it then. I've bent it into a sine of a thing, a cos of a thing, minus a sine of the second thing, cos of the first thing. So I can replace this entire expression with this particular double angle identity. So sine of, and that's my first thing. That's in the slot, the alpha slot, minus pi over 3 equals root 3 over 2. So I've successfully rendered this down into a single sine value. So all that's left to do is to solve it. So toss the arc sine over there, and it was pi minus, or phi, sorry, minus pi over 3 equals arc sine of root 3 over 2. Now the trick that gave it away was that this is in fact a special triangle ratio. Root 3 over 2 is the sine ratio of pi over 3. So this thing will be pi over 3 plus 2 pi n. Or, let's see, sine ratios are positive here, my cast rule, and here. So that's not quite a full pi, so it'd be 2/3 of pi plus 2 pi n. And this is equal to phi minus pi over 3. And this is equal to phi minus pi over 3. So I'm going to pop this one over. I end up with phi equals pi over 3 plus pi over 3 plus 2 pi n, which is just 2 pi's over 3 plus 2 pi n. And over here I have phi is 2 pi over 3 plus a pi over 3 plus 2 pi n. Phi is, that's 3 pi over 3, which is just a pi plus 2 pi n. So, because I have access to these double angle identities for sine, I'm able to take expressions that would otherwise be unsolvable, bend them around using these identities into something that is solvable, and then I can get my answer. So that's the entire point of this. If you were to scroll down after you watch this video, you should give a read through for the justification of this, and there's a little bit of talk about how to interchange these and why this one is true given these two things. So that'd be good for you to read. And then it's on to the practice questions. Good luck.